Our final speaker today is Dr. Christopher Lawley. Christopher is a gold metallurgist at the Geological Survey of Canada. Christopher has worked at the Geological Survey of Canada since 2012, and his research experience ranges from analytical method development to the application of geochemical tools as chronometers and tracers of mineral systems. More recently, Chris has been contributing to the Critical Minerals Mapping Initiative to improve critical mineral security.
Hello everyone, and welcome to this third science presentation as part of the Critical Mineral Forum. My name is Christopher Lawley, and today I will be presenting on behalf of a large team from the Geological Survey of Canada, the United States Geological Survey, and Geoscience Australia. The Critical Mineral Mapping Initiative started in 2019 and identified several broad goals for our collaboration. The first goal is knowledge sharing, and Al Hofstra from the USGS provided an excellent example of how scientists from each of our three surveys are pooling resources to update and synthesize conceptual mineral system models. The second goal is data sharing, and the results from the Critical Mineral Portal show how working together and the sum of our national data sets can have a greater impact than any individual part. This presentation focuses on another example of data sharing as part of CMMI and presents some of the first data integration steps and first prospectivity modeling results across each of our three countries. Early on in our collaboration, it was recognized that some critical minerals were more important than others, and that our knowledge of different mineral systems were at various stages of development. As part of that prioritization process, we identified that zinc mining, in particular, was important to all three countries, and that critical minerals that occur as byproducts from zinc refining were particularly susceptible to supply chain disruptions. Mississippi Valley type and clastic-dominated deposits represent two of the most important geological settings for finding additional zinc and lead resources. We know that these mineral systems are associated with large-scale fluid flow within foreland basins, rifts, or passive margins. However, the drivers, sources, and deepest pathways of these mineral systems remain poorly understood. The next few slides will show how different geological and geophysical datasets can be used to map these different components of these mineral systems. However, in order to generate prospectivity models for all three countries, we have to start bringing together our national datasets in the form of a data cube. Data cubes are multidimensional arrays that are probably most familiar to people who are used to looking at satellite-based Earth observation datasets. However, data cubes can also be constructed from other types of data, comprising text and numbers, and using irregular grids as demonstrated by this figure. Zonal statistics and spatial indexing represent two of the processes that were used to bring our national datasets together to a common grid system. Spatially indexed datasets can then be used with artificial intelligence platforms to generate predictive models. To bring all of our datasets together for the purposes of the present study, we used a discrete global grid system developed by Uber named H3. The advantages of using a discrete global grid system include that they are global in extent, they're hierarchical, they offer neighborhood tools, and they can be shared with anyone. The first step in this process, shown in the figure, is to convert the original map data and spatially index each value to a unique H3 address. Once each dataset has been spatially indexed, it can be joined using that H3 address at a particular resolution. As we spatially index more and more datasets, we start to build up a larger and larger table, as shown in step 2. This table can then be manipulated as a data cube for visualization, validation, and actually application of these prospectivity models. However, good prospectivity models start with good datasets, and we recognized early on that geological maps would represent one of the most important layers. One of our first tasks as a group was to assemble state, provincial, and territorial geological map databases and reclassify them using a new common rock legend, The new consistent formatting for rock types from all three countries allows us to generate predictive models across state, provincial, and territorial boundaries, and represents one of the most important datasets for mapping the sources and traps of basin-hosted mineral systems. Geological maps are also important because they contain a rich variety of other information that can be used as input for prospectivity modeling. Geological ages are really important for modeling the drivers and sources of mineral systems, as will be shown in the next few slides. However, to use geological ages from the provincial, territorial, and state geological maps, they had to have consistent age formatting, which is one of the efforts that we underwent as part of the current study. Geological maps also often contain descriptions of the mapped rock units. However, these rock descriptions are often in the form of unstructured text, which is difficult to work with for the purposes of prospectivity modeling. To address that issue, we developed dictionaries in French and English to extract the presence or absence of up to 17 different geological properties from the unstructured rock descriptions. These maps show areas of North America and Australia that have been described as containing carbonaceous rocks as the black polygons. Carbonaceous sedimentary rocks are relatively rare and are often missed on geological maps, but they represent important traps for MVT and clastic-dominated mineral systems. Prospectivity models are also based on geophysical datasets to map the pathways of mineral systems. For example, the lithosphere-senosphere boundary, or LAB, is rarely used for prospectivity modeling at the district or deposit scale, but can be used to map the most favorable tectonic settings for Mississippi Valley type and clastic-dominated deposits at the edges of thickened lithosphere. Paleopassive margins, shown here as the thick white lines, and faults represent other mappable criteria that can be used as proxies for the pathways of mineral systems within the crust and uppermost mantle. Once the data are spatially indexed and in the form of a data cube, we can look at the relationships between deposits and mappable criteria statistically. These probability density diagrams show how the distribution of H3 cells containing MVT deposits and mineral occurrences are distinct from the distribution of barren pixels for each country. Solid lines highlight the most favorable lithospheric thicknesses for each country, whereas dotted lines correspond to relatively unprospective areas. Overall, MVT deposits are associated with the edges of thickened lithosphere. However, the data revealed clear differences between the most favorable settings in each country, which will be further discussed in the next few slides. Satellite gravity data can also be used to map the most prospective settings for basin-hosted mineral systems at the continent scale. These satellite-based observations are important because they provide complementary view of the lithosphere obtained from seismic-based methods. The figure on the right demonstrates how areas of mass deficit correspond to cratonic areas and that the interiors of cratons are relatively unprospective for basin-hosted mineral systems. In contrast, areas of mass surplus represent anomalous density sources in the crust and uppermost mantle that are associated with orogenic belts. Because MVT and clastic-dominated deposits are associated within foreland or rift basins associated with orogens, satellite gravity data can be used as input into prospectivity models. The sources of ore-forming components represent some of the least understood aspects of mineral systems. However, brines and chloride complexes are thought to be particularly important for transporting zinc, lead, and critical minerals to their depositional site. Because basinal brines tend to form today at low latitudes, paleotectonic reconstructions are important for assessing where these brine-generated regions may have existed in the past. This map shows how parts of North America and Australia were located at equatorial regions hundreds of millions of years ago. As a result, if we have some knowledge on the age of the rock and its tectonic plate, we can actually calculate the Paleo-latitude at the timing of its deposition or intrusion. Rocks deposited at low to mid-Paleo-latitudes are considered particularly prospective for generating the brines that are required for transporting ore-forming components for MVT and clastic-dominated mineral systems. This map shows the calculated paleolatitude of each map unit based on its age and tectonic plate and tracked through time using the G-Plates application programming interface. Red areas represent rocks that were deposited at low paleolatitude. Because paleotectonic models are only available for relatively young rocks, gray areas on this map represent Mesoproterozoic and older rocks with unknown paleolatitudes. The calculated paleolatitude for each map unit was used as one of the inputs for mapping the sources and transport mechanisms of these mineral systems. Spatially indexed data sets can also be analyzed together as demonstrated by this principal component analysis biplot. This is a busy diagram showing the multivariate relationships between all of the different geophysical datasets compiled so far. However, one of the clear takeaways from this diagram is that Mississippi Valley type and clastic-dominated deposits from each region have a distinct geophysical signature. They plot in different quadrants of the PCA biplot. The clear separation of MVT and CD deposits in PCA space was not expected given that these mineral systems likely formed from similar geological processes. However, each region is separated in space and time, and the different histories recorded by these rocks in different areas represent the first-order controls on these disparate geophysical signatures for deposits and mineral occurrences. The unique geophysical signature of deposits in different regions also has important implications for prospectivity modeling. Based on these results, prospectivity models that are trained on one particular region may not be effective at predicting for the same mineral system type in other regions. To address that issue, new spatial cross-validation methods are required and were used as part of the current study to build prospectivity models that can generalize to unknown areas. Training prospectivity models is also complicated by the fact that deposits and mineral occurrences are relatively rare. To address that issue, the neighbors of deposits and mineral occurrences can be used to supplement the training set using some of the neighborhood functions that come bundled with the H3 discrete global grid system. Mixtures of deposits, occurrences, and their neighbors were all used as part of the training process. Not surprisingly, mineral deposits were identified as the best training points to identify other deposits in unknown areas. As a result, deposits, and particularly large deposits, were prioritized during the training of prospectivity models. The data cube and selected training data set were then used as input into a series of machine learning competitions in H2O. Each machine learning competition includes a variety of algorithms, such as deep neural networks, random forest, generalized linear models, and gradient boosting machines. The machine learning competitions also search over different hyperparameters for each model, resulting in hundreds of prospectivity models. The best models from these competitions are selected based on the results of the spatial cross-validation. Whilst these machine learning competitions are ongoing, gradient boosting machines tend to yield the best results. The winner of these machine learning competitions are also compared against more traditional weights of evidence-based approaches for comparison. Here we show some of the preliminary results from the machine learning competitions. The figure on the left is a success rate plot that summarizes some of the results for a single model. The y-axis on this diagram represents the proportion of MVT deposits, whereas the x-axis represents the proportion of the study area for all three countries. Good models will predict a large amount of deposits in a small area, and the area under each curve represents an overall metric for model performance. Models with areas under the curve of about 0.8 are generally considered as good model performance, whereas AUCs greater than 0.9 is generally considered as excellent. Model performance for the training set in this case is close to 1, and is thus considered excellent as one might expect for a training set. However, model performance for the test set is also high. Deposits included within the test set were not used as part of the training process, and the good model performance suggests gradient boosting machines can generalize reasonably well to unknown areas. These results are promising, but preliminary, and current work is focused on optimizing the training process so we can better make predictions in unknown areas. However, the preliminary results do show how prospectivity modeling can be used to reduce the search space for mineral exploration targeting, with over 90% of known MVT deposits occurring in less than 5% of the model space. The figure on the right shows the results from the weights of evidence model for the same mineral system in eastern North America. Areas with missing data yield posterior probabilities that are less than the prior probability and were filtered for visualization to focus on the most prospective areas. Results for the remaining map areas highlight prospective zones in the mid to eastern US, including the upper Mississippi Valley District, and a prospective corridor along the Appalachians stretching from Tennessee to Newfoundland. Here we show preliminary prospectivity model results for the clastic-dominated mineral system. The gradient boosting machine model once again yields excellent performance for the training set as expected. Model performance for the test set is also high, however the differences between the areas under the curve between the training and test set points to some overfitting. Model overfitting is a major issue for some of the advanced machine learning methods because of the relatively few deposits and mineral occurrences that are available for training. We are currently trying to address the gap between model performance for the training and test set by adjusting some of the hyperparameters in H2O and through improvements to the spatial cross-validation training procedure. The figure on the right is a map of Alaska and Yukon, showing results from the weights of evidence model for clastic-dominated deposits. Based on this image, most of the Selwyn Basin yield prospectivity values that have a higher than random chance of being mineralized. However, there are clearly zones within the Selwyn Basin that are considered as relatively more prospective. Because prospectivity models are based on a unified geological map data and reprocessed geophysical data sets, they can be used to cross national, provincial, state, and territorial boundaries to study mineral systems at the largest spatial scales. All prospectivity models are subject to a range of uncertainties that impact the interpretation of the results. Estimating model uncertainty remains an active area of research. Weights of evidence can provide some clues to model uncertainty by calculating the standard deviation of the weights of evidence transformed datasets for each H3 cell. Cells with mixed evidence tend to yield high standard deviations and can be considered as relatively uncertain, whereas map areas with only positive indicators of mineralization tend to yield high posterior probabilities and low standard deviations. Plotting model uncertainty with prospectivity estimates provide new insight into the model results. This approach is particularly important for challenging exploration settings in areas under cover that are highly susceptible to model errors, as demonstrated here for Australia. The deep yellow colored regions represent the top percentile of prospectivity scores with the lowest percentile of model uncertainty, and, as expected, correlate well with known areas of clastic-dominated deposits. Light blue areas yield some of the lowest prospectivity scores, but also are the most uncertain. These light blue areas with high model uncertainty within the interior of Australia likely map out favorable pathways identified by geophysical methods under cover and represent interesting exploration targets despite their low prospectivity scores. Future modeling efforts would benefit from integrating drill hole information to improve model performance in areas under cover. This presentation focused on some of the data sharing activities that are currently underway as part of our collaboration between the Geological Survey of Canada, United States Geological Survey, and Geoscience Australia. Data sharing provides an opportunity to study and model the sources, drivers, and pathways of mineral systems at the largest spatial scales. We demonstrate how discrete global grid systems can be used to generate data cubes from spatially indexed geological, geochronological, and geophysical datasets. The preliminary prospectivity modeling results also show how public geoscience datasets can be used to reduce the search space for MVT and clastic-dominated deposits. Future data-driven prospectivity modeling in the short term will focus on adjusting hyperparameters and the training process to limit overfitting and improve the performance of models in unknown areas. Data-driven prospectivity modeling is also being conducted in parallel with knowledge-driven or fuzzy modeling, and both methods are complementary. Results from the fuzzy models have already identified improved conceptual targeting criteria for MVT and clastic-dominated systems. Both forms of prospectivity modeling will also feed back into ongoing improvements to the critical mineral portal. Ultimately, the goal is to support mineral exploration targeting for new critical mineral deposits. These new deposits will be required to meet the forecasted demand for critical raw materials by a growing population and to mitigate future supply chain disruptions.